Oh, hey, it's Dr. J. Today we're going to learn about differentiability. So we've already been talking about the derivative and lots of different techniques for evaluating a derivative at a particular point or as a general function. But one thing that we haven't really discussed is whether or not the derivative is valid everywhere, or whether or not there are points. This is a good question. Are there values for which the derivative does not exist? Does not exist. And the answer is yes. There are. So how are we going to determine that? Well, first we're going to need another definition of what it means to be differentiable at a particular point. So the definition, a function f of x is differentiable at x equals a if f is continuous at a and the limit as x approaches a of f of x minus f of a over x minus a exists. Okay. And when I say exists, I mean the pure definition of existing that we discussed at the beginning of the semester when we first developed the concept of a limit. All right. So again, what do I mean by that? We mean equals a real number. Yeah. And that real number is called f prime of a. Yeah, so this is the number that we call it f prime of a. So this is actually a number, a value. Yeah. And it's the same value on the left and the right limits. Right? So in other words, if we took the limit from the left of all of this stuff, f of x minus f of a over x minus a, we would get exactly the same number as if we took the limit from the right of f of x minus f of a over x minus a. So all of this is just sort of encapsulating what I mean for the limit to exist, right? So it must equal a real number. It must be the same value on the left and the right. And then whatever that value is, that's called f prime of a. That is what this is equal to. If it exists. All right. If it doesn't exist, or if the function is not continuous, then we would say it's not differentiable at that point. So there are three basic types of non-differentiability. So three ways in which a function fails to be differentiable, or three ways in which a function is non-differentiable. The first is the most obvious, a discontinuity. Right? right? Because look at the definition here. The very first thing that must be true is the function must be continuous. So the most basic type of non-differentiability would be a discontinuity. All right, so something like a graph like this with a hole. So a hole. Or a endpoint we call a terminal point. So we call this a hole or a removable singularity, or a terminal point. Or the other type of discontinuity is sometimes called a jump discontinuity. A jump discontinuity. It's where the graph goes, to a certain point, and then it has a hole, and then it jumps up to another point. Okay. So these are all very common types of discontinuity. The jump could go the other way as well. Something like that. That's also a jump discontinuity. And then the hole, it could have a point, but the point may not actually line up with the hole. With a terminal point, it's just as if the graph just goes up to a particular point and then dead ends. It does not continue past that point. So these are very common types of non-differentiability, probably the most obvious one. So if you see one of these, you say it's not differentiable or it fails to be differentiable at that particular point. In a minute, I'll bust out the graphing grid and we'll be a little bit more precise with what the values are. The next one is called a corner or a cusp. So a corner or a cusp is where you have something like this. It's called a corner or a cusp. Something like that. And they could also go the other way. You could have a corner like this. You could have a cusp like this. You could have... it doesn't even have to be a very steep corner, like even a slight little bend like this. Even a slight little bend like that would not be differentiable. Okay. And then another type of cusp you might see is something like where it goes like this. And then it goes like that. So it just has a little bit of a bend to it, and then it has this little point right there. We call that a corner or a cusp. Now, I think it's obvious why the discontinuities are non-differentiable, right? It's because the graph is broken, it's not continuous, and so it's not differentiable at the point of discontinuity. But it might not be obvious why the corner or the cusp is non-differentiable. So why? All right, why is the corner or the cusp non-differentiable? Well, it has to do with this point here. So this is the point A, f of A. That's the corner. It is continuous at that point. It's not broken. So we actually do have a corner. Or a cusp. Cusp would be this one. Let me just talk about the corner here. Why would that not be differentiable? Because if you take the limit as x approaches A from the left, you get a positive number. Remember, the derivative is just another way to say the slope of the tangent line. So on this side of the corner, the slope is positive. Yeah, it's going up. But if you take the limit from the right side, you get a negative number. Yeah, over on this side. So the slope on this side is going down. The slope is negative. And so these are not equal to each other. Yeah, so the limit does not exist. So the limit is dne. All right. And so a corner or a cusp has the same basic property. On one side, the limit is usually a positive number, and the other side, it's a negative number. Okay. It could be the other way around. You could have it like this. It still doesn't exist, but now the limit on the left is negative and the limit on the right would be positive, but still they're not equal to each other. Okay. So that's the second reason why, or the second example of a type of discontinuity. The third type, non-differentiability. The third type is called a vertical tangent line. There's really only two ways that this happens. If you have this sort of S-shaped graph like that, or the reverse of that. That's about the only time this happens. So a vertical tangent line is if you took this point here, A, f of A. So again, it's at x equals A, right? All of these are at x equals A. Right? So the point is A, f of A. And if you take the limit as x approaches infinity, not infinity, x approaches A of f of x minus f of A over x minus A, that equals infinity, which technically does not exist. And even though we use the symbol for infinity, so the slope of this line here is infinite slope. It's vertical. Yeah. And so even though we use the symbol infinity, yeah, we use it quite a bit, it still technically does not exist when it refers to a value. Right? You can't say the value infinity exists. It doesn't exist. Same thing here. So in both of these cases, the limit at this point does not exist. Okay. So that's it. Those are the three types of non-differentiability that we will be talking about today. Let's go ahead and do some concrete examples with some actual functions and get busy with the mathematics. So far, I've just been drawing very loose diagrams to sort of get the idea going. So example one, given the graph of a function evaluate the derivatives or find the value of the derivatives. Find the derivative values or enter DNE. Okay, and then justify the result. All right, so give me a minute to draw what the graph may look like. All right, so there's a graph. So let's do several different versions here. Let's do f prime of -5. Let's do f prime of -4. Let's do f prime of 3 and f prime of +5. Let's assume that every box represents 1 unit. So just to mark off a scale here, we've got -1, -2, -3, -4. We're talking about this point there. -5. We're talking about that point right next to it. What else we got here? 1, 2, 3. And then 4 and 5. Now these questions can all be answered just by looking at the graph. So f prime of -5. So what is the slope of the tangent line at -5? It looks like the slope is 1. Yeah, the slope is 1 at that point. You could zoom in and see that the slope of that line is exactly 1. If it goes right across the diagonal of one box, that's a slope of 1. It's like the rise and the run are both 1. So this is a differentiable point. Yeah. In other words, this point is differentiable because we're not yet at the corner, right? It doesn't become differentiable until you get to the corner. So -4 is a corner, yeah, or a cusp. They basically mean the same thing. So the derivative there is DNE because it's a corner or a cusp. It's sort of like every corner is a type of cusp. So we always put those in the same category. Usually when you say cusp, you mean it's a little bit sharper. It's, a corner can be very dull and still be a corner. But a cusp has got a very, very, pronounced point to it. So we'll just say it's corner or cusp. I always put those in the same category. All right. So when we get to 3, this is a discontinuity. So that's also DNE. It's a discontinuity. All right. And then when we get to 5, that's not a corner. It's not a cusp. It's not a vertical tangent. It's a horizontal tangent. Now, a horizontal tangent does exist. It's equal to 0. Yeah, the slope of a horizontal tangent is equal to 0. It's a differentiable point. Not only is it differentiable, but it's the very important type of differentiable, which means that it's a maximum or possibly a minimum value on the graph. So there you go. That is your introduction to differentiability. So again, if it is differentiable, then you give me a number for the answer, for the derivative. If it's not differentiable, then you tell me dne, and then I may ask you to justify how you got your answer, how you came up with that. Same question. New graph. Something like that. So let's mark this off. 2, 3, 4, 5, 6, 7, 8, 9. 1, -2. All right, so let's do f prime of -2, f prime of 1, f prime of 4, and f prime of 9. And again, we can just read this right off the graph. So at -2, we have a vertical tangent line. Call that VT, vertical tangent line. So that one will be DNE. Vertical tangent line. Okay, at 1, we have a discontinuity. There's a hole. So again, DNE. It's a discontinuity or a hole. Back in the previous chapter, we called that a hole, or also known as a removable discontinuity. At +4, we have a horizontal tangent. HT, horizontal tangent. So that's going to be equal to 0. Now, I guess a justification could be it's a horizontal tangent, but because this lesson is on differentiability, I would prefer you to say it's a differentiable point. Because it's a differential point that happens to give us a result of 0, right? But it would still be a differentiable point even if the result was not 0, right? So the slope could be 1 or -1 or 5 or something. If you get any real number, as long as this is a real number, I'm just going to use a number sign, hashtag, whatever. So it doesn't have to be 0 to be differentiable. Right? It's just that 0 is a very easy differentiable point to spot because you can see it's a minimum value. It's the lowest point on the graph. Okay, and then this last one, 9, that's a terminal point. Terminal. A terminal point is a type of discontinuity. So you would say DNE, it's a discontinuity. Again, if you were free writing the answers, there it would be much more open to interpretation. You could say it in lots of different ways. If it's multiple choice, little drop down menu, I usually give 4 choices. So the 4 choices are vertical tangent, discontinuity, differentiable point, or the one that's not in this example, and that would be a cusp or a corner. Those are in the same category. All right, well, that does it for the introduction and the sort of warm up to the lesson. The rest of them are going to be a little bit more involved. You're not going to be able to just write the answer that quickly. Some common continuous functions with a point of non-differentiability. Differentiability. So there are some common continuous functions that you've seen in algebra class, and you'll also see them again in this class, that have a point of non-differentiability. One of them is pretty obvious, the absolute value function. That's what the graph would look like. So anytime you see an absolute value function, you know that it's going to have a point of non-differentiability. It'll be x equals 0, right? The origin. I interchange the word point with value. They don't really mean the same thing. The point is 0, 0. The value is 0. But I usually just point to it with my finger and call it a point. But when we write it out using calculus, we're really only concerned with the x value, because the x value is the most important value in determining whether or not it's differentiable. So I should just point that out. I sometimes use these words interchangeably when they don't really mean the same thing. What's another one? The cube root is also not differentiable at 0. Cube root kind of looks like that. It's like that S-shaped graph. The square root is not differentiable at 0 either, because it's a terminal point. It's a discontinuity. The graph sort of stops right there, and it does not continuously connect on the other side. One of the reasons why the square root graph is troublesome, because it is a pretty simple graph to draw, is you can't take the limit from the left because it's cut off. It's terminal right there. And then another one that might show up is the square root of the cube root of x squared. That's it. The cube root of x squared. I almost said it backwards. I almost said the square root of x cubed. It's the cube root of x squared. Again, all of these are non-differentiable at 0. The cube root of x squared, sometimes called the Gullwing function. Gullwing, like a seagull, like a seagull. Call it the Gullwing function. It has a cusp or a corner. You could call it either one. I usually say cusp. For the when it's curved, I usually say cusp. When there's straight lines, like two streets, intersecting each other, I say corner. But again, the words can be interchanged. They both are non-differentiable. So again, we have a corner. We have a vertical tangent. Vertical tangent. We have a discontinuity. And we have a cusp. So these are the four that I just sort of walk around with, when I'm, in my mathematical zone, that it kind of gives you one of each type, right? One of each of the types of non-differentiabilities. Yeah. Now notice I did say continuous, but then I said this one's discontinuous, so maybe I'll put an asterisk. What I meant by that is they're not two separate pieces. So that's what I mean about whether or not it's continuous on its domain. We're going to get into some more examples where you have the jump discontinuity, and that would be truly discontinuous when there's actually a break in the graph. So this square root graph is a special case, right? It has a discontinuity, but it's not broken. It's a different type of discontinuity. It's what we call a terminal discontinuity, as opposed to a jump discontinuity. So none of these have jumps. They're all just nice, smooth functions that have problems. I guess the best way to get into these different examples is to try a couple of them. I'm going to focus on these two right now. And we'll start with absolute value. So let's start with this one. Let's draw the graph. And then let's state the value of x where the function fails to be differentiable. And then state y. All right, so I'm kind of giving it away. It's an absolute value function, so it's going to fail to be differentiable somewhere. So what are we going to do? We're going to plot this function. It's absolute value. Let's find the corner. So the corner can be found by setting this equal to 0. Whatever's on the inside of the absolute value. We call that the argument. Abbreviated arg. So you take whatever the arg is and you set it equal to 0. This should be pretty easy to solve. In fact, you don't even need to write it down. You can just do it with mental math, and that gives you the corner. So the corner is going to be x equals -2. All right. Now let's make a table of values, starting at -2. For most of these graphs, you can, in fact, for all of these graphs, you can get away with just 2 rows in your table. If necessary, I can make the table larger, so I'll kind of leave some space down here just in case I need it. I don't think I'm gonna. I think 2 rows will be fine, especially for these very elementary graphs. Now, you're not allowed to pick the y value, okay? You have to let the corner sort of put you in the right spot. So go ahead and plug in this value. You'll notice something about the corner. The inside always comes out to be 0. So you get -2 and 5. You probably could have done that using mental math because you're always going to get the corner. You set it equal to 0. Well, because you set this equal to 0, the corner is always going to give you a 0. I mean, that's the reason why it's a corner. Yeah. So when I draw my graph, I'm going to go -2 and then 1, 2, 3, 4, 5 right here. That's my corner. Now I need one more point. You can pick any X you like and figure out what the Y is. I mean, I guess you could pick Y and then work backwards to figure out what X is, but why would you do that? I mean, I wouldn't do that. It's legal, but it's just not recommended. So just pick any X that you like. I like 0. 0 is a very nice number to plug in. You see why 0 is so nice? It makes the inside of the absolute value very easy. You don't have to pick 0. You can pick 1. That's another good choice. So I picked 0 and I got -3. Again, it's up to you. If you pick a different X, you'll get a different Y. Everything that you pick is correct as long as you calculate it correctly. So I got 0 and -3. So right here. So there's my graph. There you go. Be sure when you're doing this with your mouse that you click here first. And then click here second. All right, so you always want to click on the non-differentiable point, the corner. And it has another name. It's called a vertex. But in this particular presentation, I'm referring to it as a corner. So make sure you click there first. Okay, that's it. So let's go ahead and state the result of this. X equals -2 is not differentiable. I should say F is not differentiable. So F is not differentiable at X equals -2 because it is a corner or cusp. Okay, again, tomato, tomato, corner, cusp. Some folks might argue that they are different, but I'm putting them in the same category. Just makes it so that you don't have so many different categories to remember. It's a point, a very pointy tip of a graph. All right, let's do another one. Example 4. I'm starting with examples with these graphs of things that you've already done in, a college algebra course. So this should not be too bad. Something like that. So again, you want to set the argument equal to 0. It's also known as the radicand, or you could just say the inside. So that's going to tell us where the critical value is. Again, you could do all of this mentally. There's your mental math cloud there. And you know that your table now is going to start at x equals 3. It's always the opposite of the inside of the function. Right? If you refer this back to your algebra training, it's the horizontal shifting of the graph. So the graph has been shifted to the right 3 units. Right. Now you can plug in 3. And you probably won't be surprised that you get 0 on the inside of the cube root. And so you get 4. And again, you could probably do all of that in your mind too. So that's the whole point of using the argument, that you set the argument to 0, that gives you an x value. Then when you plug in that x value, it gives you the y value. But because you had already set this equal to 0, then most of this function, or the most important part of the function, will turn to 0, and you will just get what's called the vertical shift. So we're going to go 1, 2, 3 for x, 1, 2, 3, 4 for y. And this is going to be our vertical tangent. I do need at least one more point. All right. And again, you can pick any x you like. Now, this is a cube root, so I don't want to pick 0. Right? With an absolute value, 0 is a great number, but with a cube root, it's not so great, because look, 0 minus 3 would give you -3, and then you'd have to use a calculator, and it would get really messy. So let's just pick 2, yeah, or 4, right? In other words, pick a number that you know is going to give you a reasonable, non-decimal value. It is your choice. I mean, if you want to pick 0, I can't stop you from doing that. It would work. You get a decimal value, and then it might not be so easy with your mouse, because your mouse typically can't graph decimals very nicely. I mean, unless they're nice decimals. There are some decimals that you can plot no problem. So anyway, just do what I'm doing. Pick a number very close to the first number that you had, which was 3. So, and I don't care what order this table is in, because I'm not even going to grade the table. All right. The table is between you and your mouse, and where you're going to put the final result. So I'm plugging in 2 for x. Now remember, this is a cube root, not a square root. If this was a square root, I would stop right now, and I would say that's an imaginary number, and I would pick a different value. It would not exist on the graph. Ironically, we learn about imaginary numbers, but you have to stay in the math business for a very long time before you ever get to use them. So I take the cube root of -1, which is still just -1. Then I multiply 2 times -1. I get -2. Then I do the +4 last. So my final answer is 2, 2. So I'm going to put a dot right here. 2, 2. And this is my graph. Now remember, it's a cube root. This is sometimes called the tail, but it also has a head. All right. I'm going to say DIY. If you plug in 4, you will get out 6. DIY. So you get another dot right here at 4, 6. With the mouse graphing, once you click on the second point, so make sure you click here first, and then second. You won't have to do a third click with your mouse. You can do it on paper, but you can't, it just won't let you click a third time. Once you've clicked the second time, it's over. All right. The graphing it's pretty good. I mean, it's better than it was, even 5 years ago. And just like your phone or any other device you have, electronic, device has gotten better in 5 years, gotten faster, it's gotten smaller, right? But it's still not quite, as good as paper and pencil. It's going to be a while until, the artificial intelligence will just do all the math for you. And then you don't have to even have paper and pencil. But I'm hoping you're still at least attempting it on paper and pencil to try to, keep it real, stay human. And then use the computer as an assistant, as a tool to get a grade in the class. Nothing beats good old-fashioned, pen and pencil and paper and stuff. I'm going to stop there for the what we call non-piecewise functions. So these are continuous, non-differentiable. Let's go ahead and state the result. F is non-differentiable. It is continuous, though. It doesn't have a break in it at x equals 2 because of a vertical tangent line. So it has a vertical tangent line. You don't have to draw the tangent line, but you can imagine it's right here. It goes straight through x equals, oh, no, not 2. Sorry. I was looking at the wrong number. Hey, I'm glad I said that. It's 3. So the vertical tangent line goes right through x equals 3. You can imagine it right here. I'll draw it just for your notes. Right, so there's a vertical tangent line. We call that a VT, vertical tangent, which means it's not differentiable. It is continuous, however. So next, let's talk about piecewise functions. Two, three, four. Example 5. With piecewise functions, we're looking for everything. We're looking for all the different possibilities, but mainly what we're looking for is a jump. Just like in the previous chapter, with a piecewise function, we're looking at the two different pieces and we want to see if there's a jump. If there is a jump, a jump usually means there's a hole and a dot and there's a gap between that. We call that a jump, or a jump discontinuity. So that's what we're looking for at this value. I always give you the jump port value, which is 5. Now, I don't know if there's a jump, but if there is a jump, it occurs at this value. It's the only place where there's a break in the two pieces. Yeah. Or where there's a potential break. So this is kind of a review of what we did in the previous chapter. We were talking about continuity. And so I'm just reminding you of the concept of continuity. And in particular, now we can do the derivative. Or we can discuss the derivative. So we're going to make two pieces. Piece 1, x is less than 5. So when I make my chart, I always like to put a circle around the one that's open, because that's going to be a hole. Now, I don't know what the y value is. The x value comes usually prepackaged with the equation. You have to plug in the x value to get the y value. I'm plugging it into piece 1, so this is a whole. It's not going to be a dot. And I'm going to get 0 plus 7, so 7. So I have a whole at 5, 7. All right. Now, it might get filled in. I don't know. I'm going to wait. I'm going to wait and see. Okay. So let's just keep going. Now remember, x is less than 5, so my next point I'm going to plug in is going to be 4. Yeah. Or 3, or 2, or 1. You probably wouldn't want to plug in 3 or 2, because again, it would give you a decimal. So you could do 5, you could do 4, or you could do 1, because remember, you don't really want decimals if you can avoid them. I mean, you have a calculator, so there's no prohibition on decimals. You're certainly allowed to have them. It's just they don't work well with others. Right? They don't behave very well. So we try to avoid them whenever possible. When we start getting down and dirty with business math, we're gonna have to deal with the sort of uncomfortable, unclean values of decimals. So let's go ahead and plug in 4. I'm reusing my space here. 5 minus 4 plus 7. It's the square root of 1 plus 7. So that's going to be 8. All right. So I've got 5, 7, and 4, 8. So there's my graph. Yeah. There'll be a little tool down here that you'll pick, graphing tool, down at the bottom of your screen, and it should look like something like this. That's how it's like the half parabola. I'll call it sideways half parabola. All right, so it's kind of going sideways. It doesn't really matter which way it points. That depends on the equation that you have, the inequality that you have. All right, I better move on to piece 2. So piece 2, x is greater than or equal to 5. I wrote that one backwards. Correction. I was too busy talking and didn't notice that I had written that one backwards. They should always point in opposite directions. One of them's the left, the other one's the right. If you don't catch it at first, you can catch it before you're done. So I've got x and y. Now this is going to be a solid dot at 5. Yeah. And it may fill in the hole. I don't know. We have to look right here and ask ourselves, do they match? If this row and this row matches, well, then that's not actually a hole. It's actually a dot. So what I'm going to do is I'm going to leave it because it might get filled up with a dot. I don't know. If it doesn't get filled up, then I have this tool down here. Looks like an open hole. If that does not get filled, then I can use the hole tool and put a hole right there. Typically, I like to wait. All right, I did when I wanted to be a short video. It turned out to be a 30-minute video showing you how to use the graphing mouse. I may have to do another one of those. All right, let's go ahead and do it. So we got f of 5. Remember, we're on the correct side now. We're on the right side. So it's negative 5 squared plus 10 times 5 minus 18, which is negative 25 plus 50 minus 18, which is 7. So yes. So if the hole gets filled, then that means there's going to be no hole. All right, so don't use the hole, use the dot. All right. If these match, then fill the hole with the dot. Now, if you've already put the hole, then you can put a dot on top of the hole. I can grade it by hand. I can look at it with my eyes and see that it's right, but the computer might get confused. It's not very smart. It's fast, it's efficient, but it's not smart. So if that happens, just bring it to my attention. I'll be happy to look at it. All right, so now we're doing x is greater than 5. Again, there's no reason to go too far away from 5. So let's just do 6. You can pretty much get the whole graph done by just being, 1 unit away from the critical value, or what's called the cutoff value. Okay, so what is the y value for 6? Well, just replace the 5 with 6. The nice thing about a whiteboard is I get negative 36. Now be careful with this negative. It's outside of the parentheses, so when you square it, you're not squaring the negative, right? You're only squaring the 6. So otherwise you might do negative 6 times negative 6. I've seen people type that into their calculator and they'll get positive, and that would be wrong. So this particular case, it's outside. Plus 60 minus 18. So that's going to be 22 minus 18, which is 4. That's not right. It's 24 minus 18. I should actually be using a calculator. Negative 36 plus 60 is 24. And so the correct answer is 6. Man, I'm making all kinds of mistakes today. So it's 6, 6. And there's your other graph. Now, it's kind of hard to see what's going on here, but if you look very closely, that is a corner or a cusp. It is a very, very slight cusp. Right? If you zoomed in on it, it would go like this and then like this. This point right here. All right, if you zoomed in, magnified this point right there, it would be a cusp. So f fails to be differentiable or you could say is non-differentiable at x equals 5 due to a corner or cusp. Okay. So again, some people would call that a corner, others would call it a cusp. Some would say it's a cusp but not a corner because these are not straight lines. It's really semantics at that point. It is a pointy point that's non-differentiable. That's what sometimes we refer to it as in sort of, basic, language. Basic talk. All right, that's a two-piece function. Let's do a three-piece function. Now, this is going to be a pretty straightforward three-piece function because these take a lot of effort. And so I'm trying to keep that to a minimum. But I do want to show you what a three-piece function sort of looks like. So piece one is a parabola. Piece two is another parabola, but it's a very small piece. It's only when x is -1. I'm trying to keep the number of critical values down, or the number of cutoff values down, to a minimum. Otherwise, we could be here all day for this one lecture. It's already been an hour. So this is a three-piece piecewise function. All right. I'm going to have to move over here to -1. That's my cutoff point. And let's see what happens. So let's do piece one. Now, to speed things up a little bit, I'm only going to plug in one number. All right, -1. So f of -1. Again, this is a whole, right? Because it's less than -1. So I'm going to have -1 squared plus 2 times -1 plus 3, which is, now the negative is inside the parentheses. So that's 1 minus 2 plus 3, which is -1 plus 3, which is 2. So -1 and 2. I'm going to go ahead and exaggerate my graph a little bit so it's easier to see on the screen. So there's my whole at -1 and 2. Now, in the interest of time, I'm going to say DIY. If you plug in -2, you're going to get out 3. So I'm going to say DIY. Do it yourself. I'm not lying. If you plug in -2, you will get out +3. All right. Do it yourself. All right. Piece two. Piece two, f of -1 is a dot. Yeah. Because x is equal to -1. So remember, wholes are less than or greater than. Yeah, those are wholes. Dots are equal to. Or you could say greater than or equal to, or less than or equal to. Those would also be dots. This is just equal to. So I've got negative on the outside of the parentheses, then -1 plus 2 squared, which is -1 squared. Again, now this negative is outside the parentheses, so it's -1, -1. All right. Since it's just equal to -1, it's just one row, -1, -1. So there is a dot at -1, -1. All right. Oh, shoot. My hand. I've been really sloppy with this last row here. I accidentally erased the negative sign. So these should all be the same number. It's a cutoff value. They have to be the same number. So in piece 3, I'm going to say DIY. You just get another hole. All right, DIY. In other words, take this third piece here and plug in -1, and you will still get 2. So you get another hole right here. Now, you don't have to put a hole twice. If you already have a hole, you already have a hole. All right. Now, in this third piece, I have to do another number greater than -1. So I'm going to do 0, and you're going to get +1. And so this is the rest of your graph. It has a jump discontinuity. So f is not differentiable. Or you could say it fails to be differentiable at x equals -1 due to a discontinuity. Okay, and if I was to say what type of discontinuity, I would say this is a removable discontinuity. Right? It is jumping from here to here, but it's removable, meaning that I could fix it. Yeah, it's what we call repairable. I'm not going to. I don't want to fix it because this lesson is all about identifying the broken functions, right? Or the non-differentiable functions. So I don't want to fix it because then it won't be non-differentiable anymore, right? So it's sort of like we relish in its non-differentiability today, right? We want it to be bad, right? We'll fix them later maybe if it becomes necessary, but not today. I'm not fixing anybody today. Okay, well, I'm almost done. Example 7 now. Maybe I can do without the graphing board. So for example 7, if I want to draw a graph, I'm going to do a rough sketch graph without the precise grid. This one takes up a lot more room on the board, so back to just 2 pieces. So a 2-piece. This is the most common type, is a 2-piece. It's because we just have one cutoff value. If I start having too many pieces, it makes so many cutoff values that it would take up my whole board full of cutoff values. Not that that can't happen. It could happen. It's just not in the best interest of this lecture. Oh, and this time I got my signs right? So less than 1 and then greater than or equal to. So this is a combination of the sort of 2 possibilities, greater than or possibly equal to. And I do make sure that I have the same cutoff value, which is 1. All right, so this is kind of a long process. Let's go ahead and do all the different parts. So evaluate f of 1. Find the limit. Ask yourself, is f of 1 equal to the limit? So are they equal to or are they not equal to? I don't know. Let's put a question mark in the box here. Let's do the limit as x approaches 2 from the left. I really could have done this problem at the beginning of the lecture, but without having some practice, this problem would have been very difficult, 40 minutes ago. because all of these things I wrote down in the very beginning of today's lecture, but it was very difficult to understand what these mean without some practical examples. But now that you've seen a lot of practical examples, you'll see that this example kind of goes through everything that we've talked about. So evaluating. When you evaluate, you're just plugging in the value. And so you have to use the piece that has the equal to. So it's this piece. So that's going to be 1 plus 3 squared, which is... Did I write this down wrong? It's -1. God, I am just screwing up today. It's -1. I'm sorry. I'm not starting over again. And this is definitely not a 2. Man, I am screwing this up. -1. I think I was mixing it up with the previous example. All right, -1. So -1 plus 3 is 2. 2 squared is 4. Right. So what is the limit as x approaches -1? Well, that's also 4, which is how I caught my initial mistake. Right? If you plug it into here, on the left side, you get 1 plus 3, which is 4. On the right side, you get -1 plus 3 squared, which is 2 squared, which is 4. And so since these are equal to each other, the left and the right are equal to each other, that means that the function is continuous. At x equals -1. So yes, the function is continuous. All right. And that's about where it ends. All right. These two are going to be a little trickier. So we do know that the function is continuous. And so I said I wasn't going to draw a graph, but I probably will draw it. I'll just draw it very quickly. And so because the first 3 things have verified that the function is continuous, it means that piece 1 and piece 2 actually coincide with each other. It's actually more like this, right? You have a hole and you have a dot, and the hole and the dot coincide with each other. All right, so good. We have a continuous function. All right. If we did not have a continuous function, then I would already know the answer to these two. I should make that very clear, right? So if these first 3 steps do not give you a continuous function, they give you a break in the graph, then you can automatically answer these 2 without doing any work. You just say DNE, right? But because it's continuous, you need more space. All right. So you might actually, if you're doing your homework, you might cross your fingers and hope that this comes out to be discontinuous, right? Or maybe try multiple versions of the problem and see how it comes out. If you get one where it's not continuous, then you don't have to do D and E. You could just say they don't exist. I mean, you still have to enter D and E to get credit, but I mean, you don't have to do any work. All right, so we're going to need some more space. Let's do the limit from the left. We'll do that one first. All right. So what's that going to be? That's going to be the limit as x approaches -1 from the left. Now this is the left. right? X is less than negative 1. So it's going to be x squared plus 3 minus 4, right? Remember, we already did this. Right? We already calculated that if you plug in negative 1, you get 4 over x plus 1 because you have a double negative. Double negative becomes the positive 1. So this is the limit as x approaches negative 1 from the left of x squared minus 1 over x plus 1. Hey, we've seen this one before. This is the limit as x approaches negative 1 of x minus 1, x plus 1 over x plus 1. And so that is, oh, I canceled the wrong one. Whew. I'm losing it. X approaches negative 1 from the left of x minus 1, which is negative 1 minus 1, which is negative 2. So the left limit is negative 2. I'm just going to save that up there for now. All right. Now, if I haven't lost you out there in YouTube land, I'm trying to determine if the function is differentiable. I mean, that's what all of these problems are about today, right? I mean, that's this is not the most straightforward lecture, but it is straightforward in the point that I'm always asking the same question: is it differentiable? This is the definition that I gave at the very beginning of being differentiable. So now, if this limit on the other side, I'm just going to reuse some of this work here. If the right limit is also negative 2, then the answer is yes, it's differentiable. Right? At this value. So let's do the right limit then. Just change the minus to a plus and do the right limit. Now we're talking about the other function. So that's going to be the limit as x goes to negative 1 from the right of x plus 3 squared minus 4, right? F of negative 1 is still 4. We did that already. Right? And then x plus 1, again, double negative here. So that's the limit as x approaches negative 1 from the right of x squared plus 6x plus 9 minus 4 over x plus 1. I just multiplied out the binomial, x plus 3 squared. So that's the limit as x approaches negative 1 from the right of x squared plus 6x plus 5 for x plus 1. That's the limit as x approaches negative 1 from the right of x plus 1, x plus 5 over x plus 1. Remember, when you go to this factoring step, the denominator must cancel. So that should make the factoring a lot easier. You don't really have to guess very far away from what you already have. So I already knew it was going to be 1 times something. So the only option is 1 times 5, right? Because that's how you get 5. So that's going to be the limit as x approaches negative 1 from the right of x plus 5, which is negative 1 plus 5, which is 4. So the right-hand limit is 4. So no, f is not differentiable. F is not differentiable at negative 1. Okay. All right. Shoot, I'm out of time. We're going to have to stay after class. So keep your computers on. I'm going to do another example. Before I do another example, so we are done with this example. It is not differentiable at -1. So that part's done. The last thing that we're going to do in overtime now is finding the derivative when something is not differentiable at a point. Which sounds weird, right? Why would you find a derivative if it's not differentiable? So before I erase this, I'm just going to make a note. It's only at this one point we cannot find the derivative. So I hope that's clear about this lesson. I know when I took this class, 30 some years ago, when something was not differentiable, it sounds so final, right? It sounds like you've doomed it to the category of non-differentiable. It just means that there's one bad number. So only at this one point, -1, we can't take the derivative. However, f prime of x still exists everywhere except -1. Right? For this particular example, before I erase it. So basically, the derivative has two pieces. Yeah. The first piece is less than -1. The second piece is greater than -1. X is greater than -1. And there is no point where the derivative is is evaluated at x equals -1. Okay. And then just so that I can get this one off the board, I just want to tell you the result. The derivative of the first piece is just 2x, right? And I'll explain more about this in my next video, but I just want to get it out there. And the derivative of the second piece is 2x plus 6. All right. And so you'll have to see the next lecture to see how that works out. Okay. I just wanted to say that before I erase this example. Let's do one that we can actually do to end this lesson. So let's take a function like this. So find f prime of x and the domain of f prime. And I'll explain the domain in a separate explanation. You already know how to find the derivative, so this is kind of a review. It's the other definition of the derivative, so that would be f of x plus h minus f of x all over h. All right, and I know we've done this before, so I'm going to do it rather quickly because I know I'm already out of time and I can't film another one of these. I want to move on to the next material. So first we plug in x plus h. Yeah, then we plug in, and if you're still getting caught up on the homework, this will be a refresher. If you already know how to do this, you could probably stop the video now and say, oh, I remember that from a previous video. The numbers were different, so you're seeing another example of this. It's probably not a bad idea. This might be on the next test to see lots of different examples. 12x minus 12h minus 3 minus 12x over h. Here comes the big secret weapon here. Remember my secret weapon? I multiply top and bottom by a special form of 1. That's my special form of 1. Notice it's just exactly the same expression, but changing the middle sign to a plus. All right, and if you're having deja vu, it's because we've done this before. The limit as h goes to 0. Go ahead and do the top. You're going to get 3 minus 12x minus 12h minus 3 minus 12x in parentheses. The bottom is going to be a mess, but that's okay. It'll clean up nicely later. Now, I didn't really show all the steps for the top because I've done this before. You do the first pair, and then you do the last pair. Right? And then you be careful with this minus sign here because this minus sign is going to affect the plus and the minus signs. Coming back up here, and we could wrap this up. It's going to be 3 minus 12x minus 12h minus 3 plus 12x all over h times 3 minus 12x minus 12h plus 3 minus 12x. And this is my favorite part. It's one of the reasons why I had to squeeze this in before I hit the hour-and-a-half mark, which I'm almost to. Cancel the 3's, cancel the 12x's, and cancel the h's. And so this is your final derivative. Your derivative is negative 12 over... Now remember, the limit, I forgot to say limit. Squeeze in the limit. Guilty of forgetting my limits. When you plug in the limit, the h goes to 0. So you're going to get 3 minus 12x plus 3 minus 12x. Those are going to match. You get a matching pair. So that's going to give you a big 2. Yeah, so it's like you have an invisible 1 and another invisible 1. Right? I'm sorry to have to belabor this point, but that is such an important and often overlooked point, that those are two invisible 1s that combine together to become that 2. And then you get another canceling. The 2 cancels with the 12, and your final answer is negative 6 over the square root of 3 minus 12x. And that, my friends, is the derivative. So, before I stop this camera, we have now discussed derivatives 3 ways to Sunday, or 6 ways to Sunday, right? In other words, lots of different ways of doing derivatives, all right? And we've discussed where a function is differentiable. So, this function has a terminal point, so it is not differentiable when 3 minus 12x is less than 0. So anytime that this function is less than 0 or equal to 0. Yeah. So that means the domain is found by setting this greater than or equal to 0. Greater than 0, not or equal to. Strictly greater than 0. So 3 minus 12x is greater than 0. Move the 3 over. Divide by negative 12. Reverse the inequality because you divided by a negative. And so the domain of f prime of x is equal to negative infinity to 1/4. In other words, this is the set of real numbers that are less than 1/4, not equal to 1/4. And if you go outside of this interval, the function is not differentiable. All right, and you know, I just couldn't end the video without putting a bookend on the other end of it, right? So we start the video by saying it's not differentiable at one particular point, right? That's how I started this video. So now I've ended the video, I've ended this lesson by saying this is the opposite of saying it's not differentiable. This is saying where it is differentiable. So the domain is the set on which you can differentiate. You can find the derivative in this interval, right? I don't know if that's clear now. It's been a long time, gone on for an hour and a half, but at least I finished the section, and we can move on to something else. So do your homework, and until we meet again, I'm Dr. Jordan, and I'll see you on the internet.